Yeah, so thanks for that introduction. I'm going to talk about what MethaneSAT is and our mission, because a lot of people might not have heard of us, why we're choosing Flyte and how we're using it, and plus some of our favorite features, and then talk about some of the initial results that we've gotten by running Flyte, and then have time for questions at the end. Yeah, so MethaneSAT is an imaging spectrometer. Our goal is to reduce methane emissions from man-made sources worldwide, focusing on oil and gas initially. And we're a part of the Environmental Defense Fund, and we're a completely philanthropically funded mission. And the project is already underway. The satellite's already being built. The software team is I'm part of that. So I actually skipped that part. So I'm the lead backend engineer for the data processing pipeline, which I'll talk about. And so why methane? I'm just going to talk about this very briefly, just in case people aren't familiar. A lot of people hear about CO2 and reducing CO2. Well, methane provides a way to buy us more time to decarbonize because it has a way more potent effect on global warming initially. It's like, I think 80 times more potent than CO2, but it only lasts for about 20 years in the atmosphere. So changes we make now, we see the benefit sooner. So that's the focus of this mission. And then a quick comparison in terms of, you might have heard of some of these other satellites that have launched. So Tropomi is a satellite in the EU that tracks methane, among other things. That's kind of like a global mapper, so it can literally map the entire world's methane output. And then there's location mappers on the other side, kind of these point source mappers that look at very small areas and can get down into the weeds in terms of where the leaks are coming from. We're kind of in that middle spot where we can still image a large area, but not the whole world. And then we hope to be able to have pretty high resolution, as well as identify and quantify these different sources of emissions. And then so let's see where the data kind of comes in. So the data is collected on the satellite, obviously, and then downlinked to a base station, and then that's relayed over to our data processing platform, which is where Flyte comes in, and all this processing that we're doing, and that we're working with Harvard and Smithsonian Astrophysical Observatory and New Zealand and other partners to develop this pipeline that I'll talk about shortly. And then we're displaying all that information on a UI that our front end team is building to hopefully drive that change. So why Flyte? You've probably heard a lot of these things before. You all hear because hopefully you like Flyte. There's a lot of things that we like about it as well. We're running on Kubernetes, so being Kubernetes native, highly scalable, it's obviously a big deal. And then having the backing of originally coming out of Lyft and all these other partners like Spotify, others that are using it. It gives us confidence that running 5 million workflows at Spotify. Okay, so hopefully our use case is handled. We're not running as many workflows. We're running only about 30 to 50 a day for the different targets that we collect, but each one requires a ton of processing, thousands of CPUs running for hours doing these really heavy math and physics computations. So definitely no small workload. We needed different containers, custom containers per task, because each of these, I'll get into the different components, but there's different scientists and different science teams working on the algorithms for different portions of our processing pipeline, and they use different languages, including Fortran. So we have to support various languages, and trying to shove all that into one container is kind of probably possible, but not what we're looking to do. So being able to having the flexibility of running different containers per task is really great. Caching, obviously, no brainer, but our tasks are long running, 2 hours or more potentially, or for these things. And if you took 4,000 CPUs and then all of a sudden some downstream component failed because the container couldn't start or whatever the reason is, we don't want to have to rerun. We love the Flyte file abstraction. Not having to deal with passing files back and forth is great between the tasks. And this is last, but definitely not least, is the community here is that that's been built is phenomenal. We wouldn't be where we are in terms of testing without you all, and asking a million questions in Slack and getting answers from everybody has been super helpful. This is kind of a brief overview of our architecture. So you can see there's various pieces. The green box is kind of where the data gets saved and served up to the front end. The yellow is our kind of backbone infrastructure we're deploying to Google Cloud. And then you can see the blue boxes are kind of the different science components. We call them level 0 to level 4. And that's a NASA designation. Like we didn't pick the levels. They have very specific designations. Like level 2, for example, is methane concentration or a concentration. And then level 4 is a flux rate. So like kilograms of methane coming from per hour from a particular source. And then to get from raw to level 4, we need to organize all these tasks together. And that's where Flyte comes in. It's our backbone for orchestration and task management. So some of the features that we really like so far, and I've been leaning heavily on, these aren't necessarily the super high tech or anything, but they've been really helpful for us, is combining Dataclasses and FlyteFiles. So I'm sure everyone's familiar with FlyteFiles, but it's really nice abstraction on distributed platform to just say, yeah, I need this file, and Flyte takes care of downloading it, uploading it, and only accessing it when we need to. And we're generating large binary files, this netcdf format. So not having to worry about transferring and copying those files has been really nice. And then we're also leveraging Dataclasses, which allow you to combine, to structure a data class and define what your fields are, and then Flyte automatically serializes and deserializes it. And recently in the last few months, I forget exactly when, but they added the ability to allow FlyteFiles and Flyte directories to be part of those data classes. And that was just like a shining moment for us, because we have a lot of different inputs and various parameters that we want to associate with a Flyte file with the different outputs. And the example I have here on screen is kind of a trivial example. Like you could easily just have those 4 fields as the parameters to that level 3 gridding function. But you can imagine if you have more and more parameters and things you want to group together, these data classes are really nice for that. And we're also leveraging pretty heavily dynamic tasks, and because our algorithms can run kind of on a per pixel basis or on these sub workflows, and so we're leveraging dynamic tasks to kind of inspect the inputs, and based on the inputs make decisions and on how we want to subset the image into different chunks, span out to do parallel processing, and then kind of combine at the end. We looked at map tasks originally for this purpose, but didn't quite suit our needs. But I know there's been a lot of rework around them recently, and performance improvements and all these things, and now UI support. So it's really exciting. So we'll definitely have to take a look. I think it could be very useful for us as well. But if you're not familiar with dynamic tasks, they basically allow you, it's kind of the best of both worlds between a workflow and a task. In a workflow, you call out to different tasks, but you can't actually inspect or make decisions on the inputs. It's kind of a promise object. In a task, you just have your standard data inputs. Dynamic task lets you call out to additional tasks if you need, but also you can inspect and actually look at those inputs. So in here, you can actually see what the number A is and loop over it to call out to that T1 task. So then we're putting all that together here using launch plans and nested workflows. So we have a top level workflow for our level 0 to level 4 pipeline. And then within that, we have sub workflows for the different levels, and we're using dynamic tasks. And all these features, the composability of them really allows us to suit our use case, and I'm sure many use cases, which is fantastic. We really love the flexibility it gives us. And then expand out on this level 2 task, you can see we split the image, and then we have actually 1280, one per each column in the image. These retrieval tasks, like I call, this is where the heavy CPU, actually Fortran code, gets called and does the processing. So we've been running that on our platform, this kind of workflow from level 0 to level 2 to start. And we tried it like it's shown here with using launch plans. And we really like launch plans because it lets us obviously specify what workflow we want to run, but also we like the idea of having fixed inputs versus defaults. So we're eventually, when we're running in production and the satellite is up in the air collecting data, there are going to be analysts who are really expert in the geospatial GIS sort of world, but won't necessarily be programmers or familiar with Flyte. So kind of reducing the amount of inputs that they can change and only giving them the few knobs that they'll need to look at it and tweak is going to really valuable. But we tried it like this with 100 level 0 files, which are 10 seconds each, and we actually kind of got bottlenecked, and we're only able to run up to 500 of our available 3,000 CPUs. So that didn't quite work, and this is when the Flyte community came in handy and came to the rescue, and we ended up saying, well, why don't we just split it into have a launch plan per task, get better throughput and also better observability into kind of what is running. So that's what we've been doing, and we've been able to utilize all 3,000 of our CPUs. And that's just because that's the limit that Google has given us at the moment. It's not obviously a Flyte limitation. We're actually working with Google to get more CPUs so we can scale it even further. So that's been a really nice feature. So far we're deploying to 2 development clusters in GCP using Helm. We've scaled out the 3,000 CPUs, and we're still definitely figuring out how to optimize Flyte with our algorithms and just our Flyte deployments in general. But we're really happy with what we've been able to accomplish so far. And our goal is to use Flyte as our production task orchestrator. We're going to have 10,000 plus CPUs that we plan to use every day, processing the raw data. There'll be 30 different targets approximately that we're collecting data on every day, and that's about 200 gigs of raw data. And then I forget what our estimate is for final data. We're probably like 2 terabytes or so on the output. So a lot of data to process, and we're leaning heavily on Flyte to make that happen. And this is some initial results that we've seen. So we have a methane air operation where we actually stuck a very similar sensor to MethaneSAT on a plane, flew it around. You can see this is kind of in the corner of Texas and New Mexico in the Permian Basin. And we flew this kind of back and forth, mowing the lawn pattern, we call it, over this area, and collected a lot of really great intel. And you can see this is the output. You can see the color coding of where the methane concentrations are. And we're on the right side here. I don't know if my mouse will show. You can see that's kind of one of the really heavy leaks that we detected. And then you can also see there's kind of this blob of what we call diffuse sources, where there's a lot of emissions that might not be able to be identified to one particular source, but we identified that we can quantify the total emission there. And to put it in perspective, all the blue area here is where we flew over a course of a few hours. And this white box is the equivalent of what MethaneSAT will be able to view and scan in about 30 seconds. So fraction of the time, larger area. So we're really excited about the capabilities that this project will enable us to do, and hopefully drive the production in methane from man-made sources. So, and Flyte's going to get us there. So really excited about it. Any questions? I think that's the last slide I have.
So
this is amazing.
This is fantastic. So how big is your team that has been working on that so far?
On the backend team, there's myself and 3 others.
Wow.
And then we're working with scientists, and then the front end team is about equivalent in size. And then we have partners at Harvard and the Smithsonian National Physical Observatory and others that are providing the science expertise and example code that we're using for doing these computations, because that goes completely over my head.
Wow. And looking back on your journey so far, what was the biggest lesson that you have learned?
That's a good question. I think from the Flyte perspective, it's definitely trying to break things up into smaller tasks, using those multiple launch plans, smaller workflows, so we can kind of get that composability has been huge. That we've gotten a lot of benefit from doing that.
Amazing. I think this is fantastic to see that project. I mean, you know, if you, I mean, there's so much that there's a bigger, you know, benefit to the society. I mean, I wonder what keeps people up at night when they run such a big project. And so, so obviously you have a good solution, and I feel like you can sleep very well these days.
Yeah, lot to do, but yeah, I'm confident in the technology and our team to get us there. But yeah, lot going on.
Awesome. Any other questions for Nicholas?
I just want to say one thing, that we feel proud to be even be associated with this remotely in any way. So the community is really there to help you in any way. This is one of the biggest challenges for this century or more for humanity. So yeah, thank you for doing this work.
Yeah, and thank you for helping us, because we wouldn't be able to do it without you. So
Awesome.
A quick question. Did you experience any friction using Fortran with Flyte? And I'm also curious, like, what that development looks like, that like life cycle of interleaving or adding support for Fortran within your Flyte workflows.
I would say there was friction with just running Fortran in a Docker container in general, but then once we kind of got it kind of containerized and running, there hasn't been any friction with it calling it from a Flyte workflow or Flyte task. It's we essentially just call it as an execute. Like we have a Flyte task that's Python, gets stuff set up, and then it just calls out to the Fortran executable. We would like to maybe, I think there is a Fortran way to call it more natively from Python, but we haven't done that. We're just actually just doing a subprocess dot run command at this point to call the executable.
Cool. Thanks.
And besides Python, Fortran, is your data science research team using any other languages?
Yeah, they're using R as well.
Yeah, Kathan smiles because
Yeah.
and Niels too, because I think there's obviously in geospatial, you know, community there's a huge support of R, and I think when you go back to the, you know, back in time to MethaneSAT formats and wavelet compressions for geospatial imaging, and then also the data scientists on the geospatial side, I think R has been a really stronghold there. So maybe we can get something started on an R SDK and open source. That would be fantastic.
Yeah, I'd be happy to chat about that.
Okay, great. I think any other questions? I don't see any in the chat. Nope. All right, so we're a little bit over time, but Nicholas, this is fantastic. Thank you so much. So let's make sure that we can get the word out for what you guys are doing. It's really, really great. So kudos to you.